In qPCR, fluorescence is the language used to detect the DNA amplification. A qPCR instrument does not count the DNA molecules directly. Instead, it measures the fluorescence after every amplification cycle. As the fluorescence signal increases, the instrument tracks the accumulation of the PCR products in real time. There are two major ways to generate this signal: fluorescent dyes and fluorescent probes. Let's start with the dye-based detection. The most common example is the SYBR Green. The SYBR Green is a fluorescent dye that binds to the double-stranded DNA. When it is free in the solution, the fluorescence is relatively weak, but as soon as it binds to the double-stranded DNA, the fluorescence increases dramatically. During PCR, every newly synthesized double-stranded amplicon creates more binding sites for the dye. The more double-stranded DNA means more bound SYBR Green, and therefore a stronger fluorescent signal. However, this is the main limitation of the SYBR Green. The dye does not recognize the target sequence alone. It simply binds to any double-stranded DNA present in the reaction. This includes the correct target amplicon, the non-specific PCR products, and the primer dimers. All of these contribute to the same fluorescent signal. As a result, fluorescence alone cannot distinguish the intended target from the non-specific amplification. That's why SYBR Green assays usually include melting curves analysis to verify that the one predominant product has been amplified. On the other hand, probe-based detection takes a different approach. Instead of allowing any double-stranded DNA to generate a fluorescence, it introduces a sequence-specific fluorescent probe. The most common example is the TaqMan assay. A TaqMan probe is a short oligonucleotide designed to bind a specific sequence within the target amplicon. Unlike primers, the probe does not amplify DNA. Its role is only to identify the amplified target. The probe carries a fluorescent reporter at one end and the quencher at the other. As long as the probe is intact, the quencher remains close to the reporter, preventing fluorescence. However, during PCR, the probe hybridizes to its complementary target sequence. As the TaqDNA polymerase extends the new strand, it cleaves the bound probe. This separates the reporter from the quencher, allowing the reporter to emit fluorescence. As more target molecules are amplified, more probes are cleaved and the fluorescence signal increases. The probe has to be carefully designed from the sequence located between the forward and the reverse binding sites. Its melting temperature is typically higher than that of the primers, allowing it to remain hybridized during amplification. The primers define the region to be amplified. The probes adds an additional layer of sequence recognition within the region. SYBR Green is often a good choice when you need a flexible and relatively inexpensive assay. It is partially useful for exploratory experiments, screening multiple primer pairs, or measuring well-characterized gene expression targets. However, specificity should always be confirmed using melting curve analysis and appropriate experimental controls. TaqMan assay becomes especially valuable when sequence specificity is critical. It is often preferred for distinguishing closely related sequences, detecting specific variants, or performing multiplex assays. However, the trade-off is higher cost and the need to design and synthesize an additional target-specific probe. The type of template does not automatically determine which chemistry you should use. Whether you begin with genomic DNA or cDNA, both SYBR Green and TaqMan can be appropriate. The decision depends on the level of specificity of your experiments. For a routine gene expression analysis with a well-validated assay, SYBR Green is often sufficient. For viral load measurements, mutation detection, or amplification requiring multiplexing and maximum confidence in the target identification, probe-based assays are frequently the preferred choice. So finally, the real question is not whether you should use a dye or a probe. The real question is which strategy best suits the needs of your experiment.